All right, let's get right into it. If you've ever taken a differential equations class, you've definitely met the Wronskian. It's supposed to be our go-to tool for checking if functions are linearly independent. But what if I told you there's a huge trap, a massive misunderstanding that almost everyone has about it? Well, today, we're pulling back the curtain on the Wronskian's biggest secret. So, let's just lay it all out there. Here's the question of the day. You calculate the Wronskian of two functions, and you find that it's zero. Not just at one point, but for every single value of x. Does that automatically, 100% of the time, mean those functions are linearly dependent? You've probably been taught that the answer is yes, but it's not quite that simple. But before we get into the weird stuff, let's talk about what we can trust. There is one part of the Wronskian test that is an absolute, unbreakable promise. It's the one rule that will never, ever let you down. And just as a super quick reminder, for two functions, let's call them f and g, the Wronskian is just this little calculation you see here. It's a special formula, a determinant, that's specifically designed to sniff out whether two functions are truly independent of each other. And this right here, this is the golden rule. It is rock solid. If you calculate the Wronskian and you find just one single spot, any x value at all, where it's not zero, you can stop right there. The functions are linearly independent. Game over. This direction of the logic is always true. No fine print, no exceptions. Burn this into your brain because it's our anchor. So, with our golden rules safely in our minds, let's start pushing the boundaries a bit. We're about to look at a very clever pair of functions. On the surface, they look pretty simple, but they are going to seriously challenge that assumption we started with. Let's see what happens when we put the rules to the test. Okay, so meet our two functions. On the left, you've got f of x equals x squared. You know, your classic everyday parabola. Easy enough. But now look at g of x. It's got a split personality. When x is positive or zero, it's the exact same thing, x squared. But when x is negative, it flips upside down and becomes negative x squared. It's a small tweak, but that little flip is going to change everything. So first things first, are these two actually linearly independent? Let's check it the old-fashioned way, with the definition. We start by assuming they're dependent, which means we try to find constants c1 and c2 that make c1 f of x plus c2 g of x equal to 0. Now for positive x, where both functions are x squared, our equation becomes c1 plus c2 times x squared equals 0. Well, that means c1 has to equal negative c2. Okay, hold that thought. Now let's check the negative x values. Here, our equation is c1x squared minus c2x squared equals 0, and that means c1 must equal c2. So wait a minute. How can c1 be equal to c2 and also equal to negative c2? The only number in the universe that makes that true is 0. So c1 and c2 both have to be 0. And by the very definition, that proves it. These functions are linearly independent. All right, we just proved it. It's a mathematical fact. F of x and g of x are linearly independent. So, based on our golden rule, we'd expect their Wronskian to be non-zero somewhere, right? Well, let's do the calculation. You plug in f and g and their derivatives, and you check for positive x, you check for negative x, and you find something absolutely wild. The Wronskian is 0, all the time, for every single x. And there it is, the paradox. We have a pair of functions that we know are linearly independent, but their Wronskian is 0 everywhere. This seems to completely contradict what most of us are taught in class. So what's the deal? Did we just find a bug in one of math's oldest tools? Nope, math is safe. We didn't break anything. We just stumbled upon the fine print. You see, that rule that says a 0 Wronskian means the functions are dependent, it comes with a couple of really important but often forgotten terms and conditions. And it's all about a hidden connection to differential equations. And here is the secret, right here. The rule that Wronskian equals 0 implies dependence is only guaranteed to be true if your functions meet two big conditions. First, they have to be solutions to the very same linear ordinary differential equation. And second, this is the real kicker, that differential equation has to have continuous coefficients. It has to be well-behaved or smooth. If your functions don't check both of those boxes, then the rule just doesn't apply. So let's put our functions under the microscope and see if they meet that condition. Let's look at their derivatives. For f of x equals x squared, the first derivative is 2x, and the second is just 2. It's all continuous, smooth as can be. But now look at g of x. Its first derivative is actually continuous. It comes to a nice point at 0. But the second derivative, well, that's where the story gets interesting. This is the smoking gun. If you look at the second derivative of g of x just to the left of 0, its value is -2. But the instant you cross over to the right of 0, its value is +2. It literally jumps from -2 to +2. There's a break, a discontinuity, right at the origin. It's not a smooth function by any stretch of the imagination. And that's the whole ball game. Because our function g of x has that nasty jump in its second derivative, it is disqualified. It cannot possibly be a solution to the same smooth, continuous coefficient differential equation that our nice function f of x could be. And since that hidden condition isn't met, the whole idea that a zero Wronskian implies dependence is just off the table. The test gave us a weird result because our functions weren't even eligible to take that part of the test. Okay, so the theory is really cool, but let's make this practical. How does this actually help you when you're staring down a problem on a test? Let's turn all this into a simple exam-ready toolkit so you never get caught in this trap. Here is your foolproof 3-step game plan. Step 1, always calculate the Wronskian. Step 2, look at your answer. Can you find any point where it's not 0? If yes, you're done. Stop. They're linearly independent. That's the golden rule. But step 3, and this is the important one. If and only if the Wronskian is 0 absolutely everywhere, you have to pause and ask that critical question. Are these functions smooth enough? Could they come from the same well-behaved ODE? If the answer is no, then you might be looking at a case just like the one we saw today. So, just to really hammer it home, here are the traps to avoid. Number 1, don't just assume Wronskian equals 0 always means they're dependent. Number 2, if you do get 0, don't forget to check that smoothness condition. Also, a couple of pro tips. Make sure you fully simplify your Wronskian calculation before you declare it 0 everywhere. And of course, don't forget to look for obvious dependencies first, like if one function is just 3 times the other one. And all of this brings us to one final, bigger idea. This whole Wronskian secret isn't just a quirky math fact. It's a fantastic reminder that so many of the theorems and rules we learn have important conditions, a bit of fine print that we need to be aware of. It kind of makes you wonder, what other mathematical rules do we take for granted every day that might have their own hidden conditions? Definitely something to think about.